Welcome to the Deep Dive, where we cut through the noise to get you the most important insights from today's cutting-edge research. And wow, there is just an incredible buzz around AI agents right now.
It really is.
These systems, the ones that can make decisions, use tools, break down complex tasks, they're basically automating some pretty sophisticated operations.
Mm-hmm.
The growth is truly staggering. Recent surveys show over half of large IT enterprises are already using them.
Already over half, yeah.
And the market for this agentic AI valued at what, 5.2 billion US dollars in late 2024, it's projected to skyrocket to nearly 200 billion by 2034.
Wow.
That's not just big. That feels like a fundamental shift in how we work.
Absolutely. A huge transformation underway.
Now, the prevailing wisdom, sort of the current paradigm, is that most of these cutting-edge AI agents rely on really powerful generalist large language models, LLMs.
Right, the big ones.
The billions have been poured into the cloud infrastructure to support them, and it kind of makes intuitive sense, doesn't it? Bigger models, more parameters, more capability, or so we thought.
That's been the assumption, yeah.
But here's the provocation for today's deep dive. What if this dominant approach isn't actually the most efficient or the most economical or maybe even the best way forward for agentic AI? What if something much, smaller is actually the future?
Okay, interesting.
Today, we're taking a deep dive into some really compelling research from Nvidia. They present a powerful argument that small language models, SLMs, are in fact the future of agentic AI.
Right, from Nvidia Research.
Our mission here is to unpack why SLMs are being championed so forcefully, look at the evidence that's driving this, frankly, surprising claim, explore the challenges they face,
Sure.
and even lay out a practical roadmap for your adoption. All of this is really tailored to help you get up to speed quickly on what could be a truly transformative shift in AI.
Sounds good.
So let's start at the beginning. What's the foundational argument here?
Well, to really set the stage for that argument, I think we first need to clarify our terms a bit, just so we're all on the same page.
Good idea. Definitions first.
Okay, so when we talk about a small language model, or SLM, what we mean is a language model that can comfortably fit onto a common consumer electronic device.
Like a phone or a laptop?
Potentially, or a standard server GPU, yeah. And crucially, it needs to perform inference that's, using the model to get a response with low latency for a single user's agentic requests.
Okay. Low latency is key.
Exactly. In 2025 terms, this generally means models below, say, 10 billion parameters in size.
Got it. Below 10 billion. So what's an LLM then?
An LLM, or large language model, then, is simply any language model that is not an SLM. So anything bigger than that 10 billion mark, roughly.
Simple enough. And agent.
And when we use the terms agent or agentic system, we're using them interchangeably here. We're talking about software that has some level of autonomy, some agency. And it uses these language models, whether SLM or LLM, as its core intelligence.
Okay, that's clear. SLMs are small, LLMs are large. Agents use them to act. With those definitions locked in, what's the core claim from the Nvidia researchers? What's the bedrock argument they're making?
Right. The Nvidia researchers make a very bold assertion, really. They contend that SLMs aren't just viable, but they're necessarily the future of agentic AI.
Necessarily. That's strong.
It is, and they base this on three core values they identify. First, V1. They argue SLMs are principally sufficiently powerful, meaning they can actually handle the language modeling tasks needed in agentic applications.
Okay, powerful enough.
Second, V2. They're inherently more operationally suitable for use in agentic systems than LLMs, just a better fit for how agents work.
More suitable. Makes sense. And V3.
And finally, V3. They are necessarily more economical for the vast majority of agentic language model uses. Cheaper, essentially.
We're economical, more suitable, and powerful enough. That's quite the trifecta.
It's a really comprehensive argument they're building for a paradigm shift.
Necessarily more economical. That phrase really grabs my attention. So if SLMs are this good, this powerful, suitable, economical, what does that actually say about our current reliance on LLMs? Is it like overkill? Is the dominance excessive, maybe even misaligned with what agents really need?
Exactly. That's a key part of the argument. What's fascinating here is the idea that LLM dominance might be, as they put it, excessive and misaligned with the actual needs of these agentic systems.
How so?
Well, if you think about it, Most of the subtasks an agent performs are pretty repetitive,
Right.
right? They're highly scoped, often non-conversational. They're not these broad, open-ended dialogues or creative writing things where LLMs genuinely shine.
Right, more like processing an invoice or scheduling a meeting, specific stuff.
Precisely. And for those kinds of tasks, what you really care about is efficiency, predictability, and cost effectiveness. That's paramount.
And that's where SLMs come in.
Exactly.
Yeah.
This is precisely where SLMs shine. They offer lower latency, reduced memory needs, less computational power required, and significantly lower operational costs. The sheer scale of LLMs, while impressive, often means a huge chunk of their parameters are just sitting idle during these narrow tasks. That's just not efficient.
So it's not just about raw power anymore, but about the right fit for the job. It sounds like we've potentially been over-engineering solutions using a sledgehammer for attack.
That's a good way to put it. It's about aligning the tool to the task.
That's a powerful realization. So if smaller models are maybe the default going forward, what does NVIDIA's vision look like for the overall architecture? Are we talking a complete rip and replace or something more integrated?
Yeah, you've hit on the core idea, and this leads directly to their vision of what they call heterogeneous agentic systems.
Heterogeneous, meaning mixed.
Exactly. Imagine a more modular approach. Think of it like building with Lego bricks. SLMs are the default intelligence, the standard bricks you use for most routine or specialized tasks.
Okay.
And then LLMs are like the bigger, specialized pieces you only pull out selectively when you need them for those genuinely complex, open-ended reasoning challenges.
So a team of specialists rather than one giant generalist.
Precisely. The aim is to create agents that are both highly cost-effective and remarkably capable. And, importantly, this also promotes a more sustainable approach to AI, because you're only using the compute power you actually need for each specific task.
Ultimately, what this means for your organization listening in is potentially a dramatic shift, moving away from maybe heavy capital expenditure on monolithic LLM infrastructure
Right.
towards greater operational efficiency with these agile, specialized SLM deployments. That's not just a cost saving. That could be a real strategic advantage. It could fundamentally reshape how AI is built and deployed in your business.
It really could.
Okay, let's unpack this with some real-world evidence because this is where it gets, well, really interesting. The paper highlights some truly eye-opening examples of what SLMs can do now. Can you walk us through some of the most compelling ones? The ones that really illustrate the surprising power?
Absolutely. And the data is compelling. It really challenges some of those older assumptions about model size. You see, the scaling curve, the relationship between model size and capability, seems to be getting steeper.
Steeper meaning.
Meaning smaller models are improving faster than we might have expected. They're rapidly catching up to, or in some cases, even surpassing older, much larger models in performance.
Wow.
We're talking about key aptitudes here. Things like common sense reasoning, just that basic understanding of the world, plus tool calling and code generation, which are critical for agents to interact with external software or APIs.
Right, got to talk to the tools.
Exactly. And of course, instruction following, just doing what you ask it to do correctly. These are all crucial for agents.
So give us some examples. What are these wonder SLMs?
Okay, well, take Microsoft's Phi series. Phi 2, which has just 2.7 billion parameters, tiny by LLM standards.
Yeah?
It performs on par with models that have 30 billion parameters. But it runs an astounding 15 times faster.
15 times faster. That's not just an improvement. That's a massive leap.
It's huge. And then there's Phi 3, small, a bit bigger at 7 billion parameters. It rivals models with 70 billion parameters in language understanding and code generation tasks.
Okay, so Microsoft's showing serious progress. What about Nvidia themselves?
Good question. Their own Nematron H family. These are models between 2 to 9 billion parameters. They achieve instruction following and code generation accuracy comparable to 30 billion parameter LLMs. But, and this is key, they do it at an order of magnitude fraction of the inference FLOPs.
FLOPs being floating point operations per second. Basically, way less computation needed.
Exactly. Way less computational power required to get a similar result. It's vastly more efficient.
This is really shifting my perspective. Are there other examples?
Oh yeah, there's a model called DeepSeek R1 DistillQuen 7B. Try saying that 3 times fast.
I won't.
This 7 billion parameter model actually outperforms large proprietary models like Claude 3.5 Sonnet and even GPT-4o in certain common sense reasoning benchmarks.
Wait, outperforms GPT-4, the big ones, in common sense reasoning. That completely flips the script.
It does. And DeepMind's Retro 7.5b achieved performance comparable to the original GPT-3, which had 175 billion parameters.
Wow.
But Retro uses 25 times fewer parameters. It does this by being augmented with an external text database, which is another interesting approach.
Okay, so smart architecture helps too.
Definitely. And one more Salesforce's XLAM 28B. It's achieving state-of-the-art results on tool calling benchmarks, even surpassing frontier models like GPT-4o and Claude 3.5 in that specific, crucial agentic skill.
Tool calling is vital for agents.
Absolutely vital. So these aren't just incremental gains we're seeing. They are really demonstrative shifts in capability at smaller scales.
So if I'm hearing you right, the old idea that bigger is always better in AI, well, it might be completely outdated, at least for agents.
It certainly seems that way for many agentic tasks.
The real insight here isn't just, oh, smaller models are getting better. It feels like the return on investment on model size for agentic tasks has fundamentally flipped. You don't necessarily need the biggest brain anymore. You need the right brain for the job.
That's a great summary.
And often, that brain is surprisingly compact and efficient.
Absolutely. And it's not just about the raw performance of the base SLM either. You can enhance them further at inference time when you're actually using the model, with techniques like self-consistency, where you might ask the model the same thing multiple ways, or tool augmentation. For instance, there was a model called Toolformer, only 6.7 billion parameters.
Uh-huh.
It actually outperformed the 175 billion parameter GPT-3 on certain tasks because it intelligently leveraged API calls to external tools.
So the SLM used tools better than the LLM.
In that specific setup, yes. It shows that clever prompting and using external resources can really boost the reasoning power you get from these smaller models.
Okay, so the core takeaway is capability isn't just about parameter count anymore. SLMs now provide genuinely sufficient reasoning power for a huge chunk of agentic tasks.
That's the argument, and the evidence is mounting.
That's a really compelling case for capability. Now let's get practical. How does all this translate into tangible benefits for your bottom line for the people listening? Let's talk economics and operations.
Right, the economics. This is often the driving factor, isn't it?
Usually is.
Well, the economic argument is indeed powerful. Firstly, SLMs are just plain more economical to run.
How much more?
We're talking about inference efficiency, where serving, say, a 7 billion parameter SLM is an incredible 10 to 30 times cheaper than running a big 70 to 175 billion parameter LLM.
10 to 30 times. Cheaper in what way?
Cheaper across the board in terms of latency, so faster responses.
Okay.
In terms of energy consumption, which is huge for sustainability and cost.
Right.
And in terms of raw FLOPs, the compute needed.
Right.
This isn't just a minor saving. It's the kind of difference that enables real-time responses at massive scale, which is absolutely critical for many agentic systems.
Real-time at scale, that's a game changer.
And think about the infrastructure, too. It's inherently simpler and cheaper to maintain the hardware for SLMs compared to the massive clusters needed for the biggest LLMs.
Makes sense. What else?
Then there's fine-tuning agility. Specializing in SLM through fine-tuning. It might only take a few GPU hours.
Hours, not weeks.
Exactly. This means you can add new behaviors, fix issues, or create specialized versions practically overnight instead of the weeks or months it might take to retrain or heavily fine-tune a giant LLM. Much more responsive.
That speed is a huge advantage.
And finally, edge deployment. SLMs are small enough to run locally on consumer-grade GPUs. Think about Nvidia's ChatRTX platform, for example.
Running on your own machine.
Yes, offering real-time offline agentic inference. That means lower latency because the data doesn't travel, and much stronger data control and privacy because your data stays where you want it.
Okay, offline capability and data control are massive selling points for many businesses. That really clarifies the operational benefits. And this connects directly back to that idea of modular design, right? The Lego bricks.
It absolutely does. It enables what we might call that Lego-like composition of agentic intelligence. Instead of trying to scale up one single monolithic do-everything model,
Which gets expensive fast.
you scale out.
Yeah.
You add small, specialized expert SLMs like different types of Lego bricks.
Yeah.
This approach results in systems that are cheaper to build and run, faster to debug because the components are simpler,
Easier to pinpoint problems.
easier to deploy, and just better aligned with the real-world diversity of tasks agents actually do. Many argue this represents the best path forward for cost-effective, modular, and sustainable agentic AI.
Sustainable is a big one, too. Fascinating. And this modularity, this cost-effectiveness, it must lead to another powerful benefit, greater flexibility. What does this mean in practice for developers and organizations?
Exactly. Flexibility is huge here because the costs of pre-training and especially fine-tuning are so much lower for SLMs.
Just a few GPU hours, you said.
Right. It becomes far more practical, almost trivial sometimes, to
Hmm.
train and deploy multiple specialized SLMs for different agentic routines or subtasks.
So you can have an SLM just for email sorting, another for calendar checks, etc.
Precisely. This allows for really rapid adaptation. If your business needs change, if new regulations come in, if you just want to tweak the output format, you can spin up or modify a specialized agent practically overnight.
Wow, okay. That level of agility is impressive.
And if we connect this to the bigger picture,
Hmm.
this flexibility really fosters a kind of democratization of agents.
Democratization, how?
When the barrier to entry, the cost and complexity is lower, more individuals and smaller organizations can actually participate in developing language models specifically for agentic systems.
So it's not just the tech giants anymore.
That's the potential. And when you have more players, the resulting population of agents is more likely to represent a diverse range of perspectives and societal needs. It's not just one worldview baked in.
That could help reduce systemic biases, maybe.
That's the hope. More diversity in development could lead to reduced bias, and it certainly encourages more competition and innovation across the whole field. With more actors able to create and refine models, the entire sector could advance much more rapidly.
That's a really powerful potential side effect. And here's a crucial point the research makes, which seems obvious once you say it. Agents often only need narrow language model functionality anyway.
Exactly. Think about it. An AI agent, at its core, is often a heavily instructed and sort of choreographed gateway to a language model.
Right, you give it very specific instructions.
Even when it's using a big generalist LLM, that LLM is usually severely restricted by the prompts. It's forced to operate within a tiny little slice of its vast capabilities for that specific subtask.
So you're paying for the whole brain, but only using a tiny corner.
Pretty much. It seems clear that a fine-tuned SLM could easily handle these narrow, specific tasks, and you'd gain all those efficiency and flexibility benefits we've been talking about.
That makes perfect sense.
And this also highlights why behavioral alignment is so critical and maybe easier with SLMs.
Behavioral alignment, meaning it does exactly what you expect.
Yes, especially in how it formats its output. Agentic interactions often involve communicating with code, right? Either calling an API via tool use or parsing the model's output.
Sure, needs to be machine readable.
These interactions demand strict formatting like JSON or XML to work reliably. Now, a generalist LLM, trying to be helpful in many ways, might occasionally make what the researchers call a hallucinatory mistake. It might respond in plain English instead of JSON, or just get the structure slightly wrong.
Which breaks the agent's workflow.
Totally breaks it. An SLM, however, that's been specifically trained or fine-tuned for one single output format for that task is far less prone to these kinds of errors. It ensures much more reliable interaction with the agent's other code components.
Reliability is key for automation. Okay. It also seems logical then that agentic systems are, or maybe should be, naturally heterogeneous.
Yes, the paper argues this is a natural consequence. An agent's controlling code isn't limited to using just one model. It can choose any language model it has access to for any particular subtask.
Mix and match.
Exactly. This opens the door wide for incorporating multiple models of different sizes and capabilities within a single agent. You might have an LLM handle the core high-level reasoning, the root agency, perhaps?
The big picture thinking.
Right. While specialized SLMs could manage specific conversational elements or handle precise formatted tool calls or summarize documents in a very specific way, it's a tailored approach designed for optimal performance and cost.
A committee of experts.
A good analogy.
Yeah.
And this ties beautifully into a continuous feedback loop for improvement.
How so?
Well, think about all those agentic interactions. Each one, with its focused prompt and the resulting output or tool call, is a potential source of high-quality training data.
Data specific to the tasks your agent actually performs.
Exactly. This data can be automatically collected, obviously, with proper security, anonymization, privacy controls in place.
Crucial, yes.
And then used to further fine-tune those expert SLMs. This means continuous improvement and ongoing cost reduction become an organic part of deploying and running agents, not just some separate big effort you do occasionally.
The system learns and gets cheaper over time. That's compelling.
Very compelling.
Now, despite all these strong arguments for SLMs, we need to be balanced. There are some significant alternative views, counter-arguments that need addressing.
Absolutely. It's important to consider those.
Okay, AV1, a common one. The LLM generalist advantage. The argument is that LLMs, because of their sheer scale and maybe this hypothesized semantic hub mechanism, this central broad understanding they might possess,
Right, the idea they understand language more deeply.
that they will always have superior general language understanding, even when applied to narrow tasks. So this raises an important question. Does this superior general understanding invalidate the SLM argument for specific agent tasks?
It's a valid point people raise, and it taps into the core mystery of how LLMs work. But the research offers some strong rebuttals.
Okay, what are they?
First, regarding architectural innovation. Those popular scaling law studies, the ones suggesting bigger is always better, they often assume you're just scaling up the same model architecture, like the transformer.
Uh-huh.
But recent work on SLMs is showing significant performance benefits from using different or hybrid architectures, things like Mamba or hybrid Mamba transformer models. So the scaling rules might not apply if you change the underlying design.
So innovation could break the old scaling laws?
Potentially, yes. Second, the power of fine-tuning is often completely ignored in these broad scaling law comparisons. SLMs can be very easily and cheaply fine-tuned for specific tasks to achieve the exact reliability and performance needed. That factor fundamentally changes the performance equation for these narrow, agentic tasks.
So a general LLM might be smarter overall, but a fine-tuned SLM is better at this specific job.
Precisely. And third, remember problem decomposition. Advanced agentic systems are specifically designed to break complex problems down into simpler, manageable subtasks.
The agent does the hard thinking first.
Exactly. In those scenarios, the broad semantic hub of an LLM, its general abstract understanding, becomes much less critical because the model itself is only ever dealing with relatively simplified inputs for each step.
Okay, those are solid rebuttals. What's another counter-argument?
AV2 is about economy of scale for LLMs.
Ah, the centralization argument.
Right. The argument goes that any cost benefits of running individual SLMs are dwarfed by the massive economies of scale you get from centralizing inference on huge LLM clusters. It's harder, they say, to efficiently utilize and load balance lots of specialized SLM endpoints, and the infrastructure and talent costs for managing many smaller models would be significant.
That sounds plausible too, running one big data center versus many small ones.
We have to acknowledge that this view has validity, and the exact economic trade-offs can be highly case-specific. It depends on your scale, your tasks. However, the trends seem to be shifting. Recent improvements in inference scheduling systems, things like Nvidia Dynamo, are offering unprecedented flexibility in how models are served. This directly counters that load balancing issue for smaller models.
So the tech for managing SLMs is getting better.
Much better, and rapidly. Furthermore, independent analyses indicate a pretty consistent falling trend in the setup costs for infrastructure overall. So while LLM economies of scale are real, the landscape is evolving fast, potentially favoring more distributed modular systems like those using SLMs.
Okay, so that barrier might be lowering. But what about the last one, AV3? Inertia.
Ah, yes. Inertia of the LLM first world.
This view basically says, look, maybe an LLM agentic world and an SLM agentic world are both theoretically possible, but the LLM world simply got a massive head start. All the tools, the deployment practices, the optimization efforts, the venture capital, it's all funneling towards LLMs. Industry inertia is just too strong.
This one feels very real, doesn't it? It's like trying to get a supertanker to change direction mid-ocean.
Exactly. How do you possibly overcome that kind of established momentum, even if SLMs are technically better or cheaper?
That's an excellent analogy, and we absolutely have to acknowledge the reality of this inertia. It's a significant factor.
So is it game over then?
Not necessarily.
Yeah.
So the argument from the researchers is that the combined weight of the advantages we've discussed, the demonstrated power, the really significant economic benefits, the vastly increased flexibility and agility of SLMs, is strong enough that it could plausibly overturn this inertia over time.
So the benefits outweigh the switching costs eventually.
That's the bet. Think of it perhaps not as one supertanker versus another, but maybe the LLM supertanker versus a whole nimble fleet of specialized SLM vessels. Collectively, they might be able to outmaneuver the larger, slower giants, especially as the AI landscape keeps changing rapidly.
A fleet versus a supertanker. I like that.
Yeah.
Okay, so if SLMs are so great, the arguments are compelling, the rebuttals seem strong, why aren't they everywhere already? What are the real practical hurdles holding back widespread adoption right now?
That's the million-dollar question, isn't it? And the research does identify some key practical barriers that exist today.
What are they?
First, B1, upfront investment. Just huge capital bets have already been placed on centralized LM infrastructure. Billions and billions. This naturally leaves development focus, tools, everything towards that paradigm, not necessarily towards decentralized SLM or efficient on-device inference. The money flows where the bets were made.
Follow the money. Makes sense.
Then there's B2. Generalist benchmarks. How we measure these models matters. SLM development often ends up chasing the LLM playbook, focusing on the same broad generalist benchmarks like MMLU or HLM.
Where bigger models naturally do well.
Right. Instead of focusing on benchmarks that specifically measure agentic utility, things like tool use accuracy, task completion rates, cost per task, which are the areas where SLMs really shine, we're potentially measuring the wrong thing for agents.
Interesting point. What's the third barrier?
B3, lack of awareness. It's simple, really. SLMs just don't get the same level of marketing hype and press attention as the big flagship LLMs. Everyone knows GPT-4 or Claude 3.5. Fewer know about Phi 3 or Nemotron H, unless you're deep in the field.
Okay, so existing investment patterns, potentially misaligned benchmarks, and just less public awareness. Those are definitely important practical hurdles. But are these fundamental flaws in the SLM approach itself, or are they things that can be overcome?
That's the crucial distinction. These are indeed important practical hurdles, but the researchers argue strongly they are not fundamental flaws of SLM technology or the SLM-centric agent vision. They are addressable challenges.
How are they being addressed?
Well, progress is already being made. We mentioned advancements in inference scheduling systems like Nvidia Dynamo. Those are actively reducing barrier B1, the infrastructure challenge, making it easier to manage diverse models.
Okay, tech is catching up.
Barrier B2, the focus on generalist benchmarks, is gaining recognition within the AI research community.
Sure.
There's a growing push for more relevant, task-specific, and agentic evaluation metrics. That tide is slowly turning.
Good.
And barrier B3, the lack of awareness. That will likely diminish naturally over time as the clear economic and operational benefits of using SLMs in agentic applications become more widely understood, demonstrated, and frankly, felt on the bottom line by more companies. Success breeds awareness.
Money talks eventually. Okay. So, if you listening now are convinced that this shift to SLMs is something worth exploring for your own agentic applications, the paper provides a really concrete, practical 6-step algorithm. It's basically a guide to help you potentially switch painlessly from LLM generalists to SLM specialists.
Yeah, and it's a very practical roadmap.
An LLM to SLM conversion algorithm. Let's walk through it quickly because this is fantastic practical advice for you. Step 1. Secure usage data collection.
Right. First, you need the data. You start by instrumenting your existing agent, even if it uses an LLM now, to log all the non-human interactions.
What kind of interactions?
Prompts that the agent sends to the LM, the responses it gets back, any tool calls it makes, maybe latency metrics for each step. But critically, set up encrypted logging pipelines right away. Anonymize user data rigorously to protect privacy. That's non-negotiable.
Absolutely critical. Okay, log everything securely. Step 2, data curation and filtering.
Now you've got the raw logs. Once you've collected a decent amount, the paper suggests maybe 10,000 to 100,000 examples, which isn't huge for fine-tuning smaller models. You need to clean it up. Meticulously remove any remaining sensitive data, PII, PHI, proprietary business info.
Wow.
You can use automated tools for masking or removal. For application-specific inputs, maybe you paraphrase them to hide sensitive details while keeping the structure of the request intact. The goal is clean, safe data.
Got it. Clean and safe. Step 3, task clustering.
Okay, now you analyze your clean data. Use unsupervised machine learning techniques like clustering algorithms on the prompts and the agent's actions. The goal is to automatically identify recurring patterns.
Finding the common jobs the agent does.
Exactly. What are the common types of requests? What operations does it perform frequently? This helps you define distinct tasks where a specialized SLM could potentially take over. Maybe it's intent recognition or summarizing certain documents or generating code for specific APIs.
Define the roles for your future SLM specialists. Makes sense. Step 4, SLM selection.
Now that you have your tasks defined, you select one or more candidate SLMs for each task.
How do you choose?
Look at the SLM's inherent capabilities. Is it good at coding or reasoning or following instructions? Check its performance on relevant benchmarks, if they exist, for that specific task type. Consider its licensing. Can you actually use it commercially? And importantly, its deployment footprint. How much memory and compute does it need? Will it fit your infrastructure?
Match the SLM to the task and your constraints. Okay. Step 5, specialized SLM fine-tuning.
This is where the magic happens. You prepare task-specific datasets using your curated data from Step 2, tailored for each task cluster from Step 3. Then you fine-tune your chosen SLMs from step 4 on this data.
Training them to be expert.
Exactly. You can use efficient techniques like LoRa or QLoRa to make this computationally cheaper. Or, in some cases, you might use knowledge distillation, basically. Train the small SLM to mimic the outputs of a more powerful generalist LLM, but only on your specific task data.
Teaching the student SLM from the master LLM, but just for one subject.
Good analogy. And finally, step 6, iteration and refinement.
This isn't a one-off.
Definitely not.
Yeah.
You need to establish a continuous improvement loop, periodically retrain your specialized SLMs, and maybe any routing models that decide which SLM to use, with new data collected via step 1.
Keep them sharp.
Keep them sharp, adapt to any new patterns in usage, maintain performance, and continue to optimize for cost and efficiency. It ensures your agents remain cutting-edge and cost-effective over time.
That's a fantastic, actionable roadmap. Secure data, curate it, cluster tasks, select SLMs, fine-tune them, and iterate. Brilliant.
It provides a clear path for organizations looking to explore this.
So wrapping up, we've covered a really powerful argument today. We've seen evidence suggesting that small language models aren't just some niche alternative, but potentially the necessary future for many, if not most, agentic AI applications. They offer potentially incredible power, very significant economic benefits, and vastly increased flexibility compared to the current LLM giants.
Yeah, the shift they describe, moving from these monolithic LLMs towards more modular, specialized SLMs within agentic systems, it really isn't just a technical refinement or optimization.
What is it then?
It feels more like a profound move towards a potentially more sustainable, more adaptable, and maybe even a more democratized AI future. It allows intelligence to be deployed much more precisely, more efficiently where it's needed.
More democratized. That brings us back to that interesting potential. And it leads us to a final provocative thought for you listening. Considering this potential for many more individuals, more organizations, to develop specialized AI agents using these more accessible SLMs, what new kinds of innovations or societal impacts might we see emerge? Things that are perhaps currently unthinkable with only large, centralized LLMs dominating the landscape.
Interesting question.
What does this shift mean for the accessibility, the control, and maybe even the diversity of AI in your hands, in your organization, and in society as a whole? Something to ponder.